Okay, let's start with a simple example, rolling a die. What value do we expect to get when we roll a die? Well, we've got some possibilities here. 1, 2, 3, 4, 5, and 6. These are the outcomes that we have available to us. Let's go ahead and just lay these out. You guys know the numbers 1 to 6, but these are what could happen. What do we expect to happen? Well, we expect it's going to be one of these. Expected value lets us take this situation and compress 6 numbers into just one number. So what we're thinking about here is not what we actually get, but an average of what we're going to get. So we have these outcomes we might end up at. Let's try and line these up reasonably well. Right, we've got these possible outcomes that we could get to, and we've got some probability of getting to each one of them. Now, in the case of a die, we know the probability of each one is equal. So what we're going to do is we're going to say 1 plus 2 plus 3 plus 4 plus 5 plus 6. Add that all up together, and what do we have? We've got 10, 15, 21. So if we were to roll the die 6 times and we got each of those 6 answers, we would have a total number of upward facing numbers that add up to 21. But we're going to divide that by 6 because we have 6 die. We want to know what is the average outcome we got on all of these. And that's going to be, what, 3.5. Right? It's going to be, we can really simplify this. 1 plus 6, right? Average that out, that's 7. 2 plus 5, that's 7. 3 plus 4, that's 7. Halfway in between each of these is 3.5. That's our average overall. Right? That was just me doing some, I guess, Common Core math, so don't sweat it if I lost you there. But our average of these 6 numbers is 3.5. Right, so if we roll the dice, what do we expect? Well, let's try this. We get a 1. I'm going to keep a tally. Roll it again. We get a 4. I'm going to roll a bunch. Save some time. What do we got? We've got another 4. We've got a 2. We've got a 6. Another 4. Oops, I rolled that one. Doesn't really matter. 5, 2, whatever that was. That was another 4. Couple more 4s, and a 1. So we rolled 10 dice. What did we get? Well, we've got, what's this? 2, 6, 24 is 30, 35, 41. So we got 41 over 10 dice. Make sure I can count right. Divide by 10. 10 with a 0. And our average there, did I say 41? I think I said 41. 41, so our average is 4.1. So it's not exactly the 3.5 that we expected. But what would happen if we kept doing this? If we were to roll these dice over and over and over again and add up all of what we get and take that average across a million dice rolls, what we're going to end up doing is getting very close to that 3.5 with a large enough number of rolls. Right? So what we mean by expected value is this average across many possible repetitions of some uncertain outcome. Some outcome where we know it could be 1, 2, 3, 4, 5, or 6, but we don't know which it's going to be on any particular roll. Right? We got 1 there. We couldn't have known anything more than there's a 1/6 probability of that happening. So, expected value, this average was nice and easy. So let's make it a little bit more complicated. Let's say we're playing a game where whatever we roll on red is going to be one part of our score, and then any number on purple that's less than 3. So 1 or 2 on purple. And if we get more than 2, then we're going to re-roll. So if we do that, 6 is bigger than 2, bigger than 2. We got a 2. So our score there is 5. Keep doing that, what do we get? Oh, hey, we got another 5. Is 5 a crazy outcome? Well, we could just keep doing this, which is going to take us a long time. We could get the computer to simulate it, which gets the computer to do a lot of effort, but takes very little time on your part and mine. But for this case, what we're going to do is we're just going to set up the math, right? We're going to try to solve this with our brains. So in this case, we still have this outcome, but then our purple could be 1 or 2, and if it's anything else, then we're going to redo this, right? So we got 1, 2, 3, 4, 5, 6. Redo the purple roll. +1 or +2. So we're going to have 2 branches off of each of these. So all of our possible rolls, we're going to get whatever we get on red. So maybe we get a 4, we're on this branch. And then we're going to roll this until we get a 1 or a 2. We've got a 5 again. 5 looks really, really tempting. And here's part of the reason it's so important to understand the idea of probability and expected value is you saw we got 3 out of those last 4 rolls added up to 5, and our human brains look at that and see a pattern, right? What do we think is going to come up next? My brain thinks it's going to be 5, but what does math think is going to be next? Well, maybe not 5. Let's just check. It was a 4, right? So my brain was expecting a 5. We didn't get the 5. How crazy was that outcome is the real question. So we've got all these possibilities. Now we're going to take an average of these outcomes, right? So what do these add up to? We got 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8. Right? So we can add all those up and ask what's the probability of getting into each one. In this case, they're going to be equally likely. Right? We're dealing with dice. I'm hoping these are fair dice. So in that case, it's still going to be a relatively simple average. Now, let's think of something a little bit more muddy, right? Something where we don't have the same outcome of everything happening. So let's take the example of driving. Driving is something where we're dealing with uncertainty, and when we're driving, we have 2 basic outcomes: wreck or safe. And within wreck, we might think about a wreck where it's your fault versus the other driver's fault, but let's not even worry about that. What we're going to think about here is our outcome and our probability. What's the chance that we drive somewhere and we get there safe? Well, most of the times when we drive, we get where we're going. It's going to be very high. Now, driving is a very dangerous thing, statistically speaking, even though, anytime you roll the dice, you expect to get some particular thing that involves you getting to where you're going, but we know that in practice, sometimes you get some weird outcome that isn't safe. Maybe the equivalent of, the die spinning on its corner or whatever. So, we might wreck, we might be safe. The probability of being safe is very high. Let's just call it 95%, just to make the math easy. It's probably closer to 99% for most of the trips that we take, but it's not 100%, right? We know that accidents do happen. We know that more accidents happen when we're driving than when we're, say, taking a plane or taking a bus. But we've got some probability, and therefore we know the probability of the other outcome has to be 5%. Now, really quick digression, 0.95, this is the same as 95%. What this means is, if we have, say, 1.0, that's 100%, and we want to know some outcome, it's a lot easier to say 1 times, whatever outcome equals whatever that outcome is. And it's easy to say 0.5 times that outcome is 1/2 of that outcome. Percentage, it doesn't mean anything different. It's just a slight nuisance. Mathy people are going to tend to do it this way. If nothing else, you're going to look a little bit better at your job interview if you're referring to probabilities this way rather than with the percentage, even though it means exactly the same thing. People are weird. So, we've got these outcomes, we've got these probabilities. Now we need to assign some values to these outcomes. We want to know how safe are we on average. So we could think about this as being some big negative number. Let's think about this as an insurance company. So if someone wrecks their car, what happens to you as the insurance company? You're going to have to pay a big claim. So maybe that ends up costing you $50,000. And if they're safe, it's going to cost you $0, right? From the perspective of the driver, we might think of this as something like, well, they're going to miss work, they're going to have a whole bunch of problems. Maybe it's a really big negative thing. And if they go somewhere, maybe it's a big positive thing. But let's stick with something relatively simple. So, we want to take the average of these outcomes the same way we did with rolling the dice, but now we're not going to take an equal average because most of the time we don't get in the wreck. So one way we could do this is we could do this 20 times, right? So 1 out of 20 times we have a wreck, so we could add up, what I say, minus 50 plus 0 plus 0 plus 0 plus 0 all the way down. And we're going to get minus 50 divided by 20. Right, this is going to give us the exact same math, but let's, just for the sake of getting this right, let me pull out my calculator so I don't get this too wrong. So we've got $50,000 loss times 0.05, $2,500. Let's put that in red. So minus 2.5K, and then 0 times 95 is nice and easy. That's 0. We add these up, right? We're going to be adding up 5% probability plus 95% probability. We're getting 100% probability, and we add these two up, and we're going to get negative $2,500. So, this probability, maybe this is the probability that someone gets in a wreck in the next year. Right? So someone's going to have a 5% chance of getting in a wreck in the next year. The expected cost to the insurance company, if this is the claim they expect to have to pay out, they're expecting a cost of $2,500. So what do you do if you're the insurance company in this situation? Well, you're going to set the premium. And the premium has to be greater than $2,500 so that you're covering the cost of the claim on average. Right? If you've got 20 customers like this, most of them don't cost you anything, but enough of them do that you need to be getting enough revenue on average to cover that cost. So, expected value. The big idea here, we're averaging, and we're weighting that average by the probability of different outcomes. So, the math hopefully is not too scary. Let me pull up a spreadsheet here. Can you see this? Cool. So, probability. Now we can go from a relatively simple example to something a little bit more elaborate. So, let's say we've got 4 different outcomes. Let's say, I don't know. Let's say 3 outcomes, right? Maybe you got an outcome where you win $20, one where you lose nothing, and one where you lose $20. Whoops. That's our outcome. So win, neutral, lose. And we need some probabilities for this. So if there is, let's say, a 1/3 chance of each, then we can say our weighted value is going to be that probability times that value. Do that for each of these. And then we're going to have our expected value is the sum of those weighted possible outcomes, right? So the value of the outcome weighted by the probability gives us the contribution to our expected value. And in this case, since everything is evenly balanced, our expected value is 0. Now, if you're running a casino, you're not necessarily going to do it like this. You're going to find a way to reduce your possible losses. You're going to do things like with roulette, there's the little green things that mean there's a slightly higher chance of losing than there is of winning. So if this is instead of 1/3, instead of 10 over 30, it's 9 over 30. And then this is 1 minus this, right? So our total adds up to 100%. So we have a slightly lower chance of losing. We have a slightly higher chance of breaking even. The outcome here is that on average, we're getting a little bit of extra money, right? And this is the basic business model of a casino. Sometimes they win, sometimes they lose, but they play enough that they're getting close to the expected value. So they set the rules so that that expected value is positive. All right, so that is, got this. That is expected value in a nutshell. There's going to be some more videos after this explaining this, going a little bit deeper into the math of it. And as always, if you have questions, let me know in the usual places, and I will talk to you in the future.